Hello, I'm recording this video because of an email from a friend who is watching my videos and making good comments. And one of the comments last time was that I explained during a lecture that you can perform such integral using hyperbolic functions, and he thinks that I should have said trig functions. And once I thought about his remark, I realized the problem was that the answer itself requires inverse hyperbolic functions rather than hyperbolic functions, although when you do the integral you can use the hyperbolic functions. And I actually wanted to go over the two different methods of calculating this integral because some of you might want to know. Okay, so first, the problem arises from the simple question of what is this portion of the parabola. So you have the very simple looking y equals to x squared parabola, and you take the portion from 0 to 1, and we want to ask the length of that curve, which seems so basic that we should know, and indeed we do know, except that the answer is more involved than what one would expect. Okay, so I assume that you've learned the arc length formula, which is if you have a function f of x over the interval a to b, you have to integrate square root of 1 plus f prime of x squared inside the square root, and then you integrate by dx from a to b. Applied to our case, the derivative of x squared is 2x, and the interval is from 0 to 1, so this is what you have. And let me first do the trig substitution method. And the standard way you do it is when you have a squared plus x squared, the trig substitution usually says you want to do x equals to a times tangent of theta, because if you have tangent squared plus 1, it turns into secant squared, and it becomes easy to get out of the square root because the square root will cancel this squared. So what we want to do is, because I want this to be tangent squared and then plus 1, we will take x to be half of tangent of theta. That makes the derivative of x, dx, equals to 1/2 secant squared of theta d theta. That's the derivative. And also, if you have 2x, that's just tangent theta. That means this will become tangent theta as we want, so that the entire thing will become secant squared. And then for definite intervals, you also have to change the bounds. When x is 0, that means 0 is equal to tangent of theta. And we know that tangent of 0 is 0, so that's good. But when x is 1, you plug in 1 here, is 2 times 1 equals tangent theta, so you have 2 equals to tangent theta, which will make the theta be tangent inverse of 2. Okay, now let's try to rewrite the integral using these values. So it'll be, the integral would be from 0 to tangent inverse of 2 of square root of 1 plus tangent squared of theta times 1/2 secant squared of theta d theta, because dx is replaced by this one. You can pull the 1/2 outside, and because 1 plus tangent squared is secant squared of theta, and by the way, secant squared of theta will cancel the square root, and you will just write down the secant of theta. And you always have to be careful when you take some square outside the square root, because sometimes the thing you took out could be a negative value, and then in that case you have to put absolute values. Here, in the interval from 0 to over here, the secant is always positive, so we don't need to put absolute value here. So it's just secant of theta times secant of theta squared d theta from 0 to tan inverse of 2. And and that integrates to from 0 to tan inverse of 2 of secant cubed of theta d theta. Now that integral, secant cubed of x dx, is actually not so easy. It requires integration by parts and some additional ideas. So that's why I made a separate video for that. And the result of that video says that secant cubed of theta would integrate to secant theta tangent theta and ln of secant theta plus tangent theta plus c. And there's an extra 1/2 there. So it will be over 1/4 of secant theta tangent theta plus ln of secant theta plus tangent theta. And you have to plug in tangent inverse of 2 and 0. Okay, when tangent inverse of 2 goes into tangent theta, they cancel and it will create 2. That's good, except that for secant of theta, we need to do some more work here. So let's erase something here and talk about that. What is secant theta, secant of tangent inverse of 2? Well, because secant theta is square root of secant squared, and you can rewrite this as 1 plus tangent squared of x. That's going to be square root of 1 plus tangent of tangent inverse of 2. So that's going to be canceling, which will give you square root of 3. Oh, sorry, this should be squared, so that should be square root of 5. So there we have it. Whenever this is plugged into secant, it's square root of 5. When this is plugged into here, it's 2. So that's going to say 1/4 square root of 5 times 2 plus ln square root of 5 plus 2. And then when you plug in 0, tangent 0 is 0, and 0 times anything is 0. Tangent 0 is 0. Secant of 0 is 1, but ln of 1 is 0. So both of these terms will become 0 when you plug in 0. That means there's nothing that you get from plugging in 0. So that's the answer. Okay, now let's go for the hyperbolic functions. Now, if you don't know what hyperbolic functions are, it's the even and odd part of the exponential function. If you have any function, the even part is f of that value plus f of negative of that value divided by 2. And this will be an even function. So that's called a cosine hyperbolic, and the odd part is called the sine hyperbolic. The reason for such a name is from the Euler's identity, that you can see that the Euler's identity version of sine and cosine functions look very much like these. And because they only differ by some factor of I, a lot of the formulas that you have in the trig function world has a corresponding formulas in the hyperbolic function. So for example, we know that, this should be squared. We know that cosine squared plus sine squared is equal to 1. In the hyperbolic functions, it's really cosine squared minus sine squared is equal to 1. We know that sine differentiates to cosine. Sine hyperbolic also differentiates to cosine hyperbolic, as you can see if you differentiate this directly. And also, there's a double angle formula, no, half angle formula actually, this is called half angle formula. Cosine squared of theta is equal to 1 plus cosine 2 theta over 2. there's this trig identity, and you have a corresponding one for cosine here as well. So these are the things that we will be using. And the hyperbolic substitution works like this. Because, again, the idea is something squared plus 1, if you can rewrite this into something else squared, then that's going to cancel the square root, right? So you want to set x equals to 1/2 of sine hyperbolic of u, because then 2x would be sine hyperbolic of u, right? So that this would be sine hyperbolic squared plus 1 will give you cosine hyperbolic squared, and that's going to cancel the square root. Moreover, if you differentiate this, dx is 1/2 cosine hyperbolic of u du. And then we also need to figure out the bounds. So when x is 0, that would mean that 0 is equal to sine hyperbolic of u. And as you can see, if you plug in 0, you get 1 minus 1 over 2. So sine hyperbolic of 0 is indeed 0. That means u can equal to 0. What about x equals to 1? That would mean that when you plug in 1, 1 times 2 is 2. 2 is equal to sine hyperbolic of u. And that would mean that u is equal to inverse, u is equal to sine hyperbolic inverse of 2. Okay, so now we are going to change this integral with respect to u. It's 0 to sine hyperbolic inverse of 2, square root of 1 plus sine hyperbolic of u squared. And then du would be replaced by 1/2 cosine hyperbolic of u du, where you can now move the 1/2 in front. This will become cosine hyperbolic squared. Again, it's positive, so it will be just cosine hyperbolic of u. So you end up with the integral of 0 to sine hyperbolic of inverse of 2 of you have cosine hyperbolic squared of u du. Okay, and now we can use this formula to rewrite it as 1/2 integral from 0 to sine hyperbolic inverse of 2. And then you have 1/2 plus 1/2 of cosine hyperbolic of 2u du, whose integral now is 1/2 times 1/2 integrate by u, so it's 1/4 of u. And then if you integrate cosine hyperbolic 2u, this 2 will give you another 1/2, so it's 1/2 times 1/2 times 1/2, so it will be 1/8. And cosine integrates to sine hyperbolic of u. That's because if you differentiate sine hyperbolic, you get cosine hyperbolic. So the antiderivative should be that. I forgot to put the 2 there. And then now what you have to do is you have to plug in sine hyperbolic inverse of 2 and then 0. Okay. So I think at least until this part, the integral is a lot easier than the other one, because if you actually try to do the secant cubed of x, it is very involved. So you get the answer somewhat more quickly. Now, how do you actually get the value that we got before? Well, to do that, we will first need the double angle formula. And remember, sine 2 theta is 2 sine theta cosine theta, right? There's a corresponding one for the sine hyperbolic of u. So sine hyperbolic of 2u is equal to 2 times sine hyperbolic of 2u times cosine hyperbolic of u. Okay? So it's going to be this value. And then, therefore, when you plug in sine hyperbolic inverse of 2, this is going to get in here and there. Of course, sine hyperbolic of sine hyperbolic inverse of 2 would be 2, whereas we need to figure out what that is. So let's figure that out. If you have cosine hyperbolic of sine hyperbolic inverse of 2, that's same as square root of cosine hyperbolic sine hyperbolic inverse of 2, which is square root, this should be squared, and then that's same as 1 plus sine hyperbolic of sine hyperbolic of inverse of 2, this thing squared. So again, that gives you square root of 5, right? Okay, so you get square root of 5 that way. Therefore, when you have sine hyperbolic of twice of ln of inverse, twice of sine hyperbolic inverse of 2, then it will become 2 times 2 times square root of 5, which is 4 radical 5, and there's a 1/8 there, so it will be 1/2 radical 5. And then you will have 1/4 of sine hyperbolic inverse of 2. And for that one, unfortunately, we can get the actual value of sine hyperbolic inverse of 2 by solving an equation. Let me show you that as well. So because sine hyperbolic inverse of 2, if this is equal to, let's say, t, then 2 is equal to sine hyperbolic of t, which is e to the t minus e to the negative t over 2. And you can bring this over here, so it's 4 equals to e to the t minus e to the negative t. And then you can, again, do change of variables to say this is like s minus 1 over s equals to 4. If you multiply by s both sides, it's going to be s squared minus 1 equals to 4s. So s squared minus 4s minus 1 would be 0. And then the solution using either completing the square or quadratic formula will give you 2 plus minus square root of 5. And because we know that this value is positive, it should be the plus 1. So that's what we have, and we're not done yet because we want to find the value of t, right? So since s is e to the t, we know that t must be ln of 2 plus radical 5. All right, so that is the value of sine hyperbolic inverse of 2 as a number. So it will be 1/4 of ln of 2 plus radical 5, and then plus. And when you plug in 0, both are 0, so that's another answer. Now, this looks a little bit different than what we had before, but you'll be able to show that the two things are equal.